Welcome to Empowered Learning. This video will be about using integration to find areas of surfaces of revolution. So what we're going to talk about in this video is how we can use integration by taking some function and acting like we are going to take the profile of that function and rotate it about an axis so that we can come up with some shape. And instead of looking at the volume for that shape, we're going to look at the area that is on the outer surface of that shape. Hence, why we call this areas of surfaces of revolution. Okay, so we want to imagine that instead of trying to find the volume of a ball or cone head of an airplane or missile with some arbitrary solid, we just want the outer surface of those things. Okay. Now, one way we can imagine forming the surface area of an object like that is to imagine some general curve, okay? And I'm just, we can think of like a line, okay? So I'm going to go down to these figures here, try to explain what's going on. So if we took the example of just a horizontal line segment, and we took that and we rotated about the x-axis like what you see that I've drawn here, then it basically looks like a tube. So kind of like a paper towel tube or a toilet paper tube, where of course you have the cardboard on the outside or whatnot. And if we wanted to know what that surface area was, what we could essentially do is take that cardboard tube, if we want to think of it that way, and just cut it. Okay, so if we cut it right where this line segment PQ is and roll it out, what it will basically look like is a rectangle. Okay, and we know that delta x would represent the quote unquote the height, or we may want to say the width of this particular tube, and this 2 pi times y, of course y would be the radius or the distance from the axis of rotation up to the actual surface. That would be its height or its length, depending upon how you want to interpret that. The main thing here is that if we wanted to know the surface area of this tube-like figure, then essentially all we would have to do is know the area of a rectangle to be able to do it. Okay. Now, of course, the formal name for this would be a cylinder, and we would want to know what the surface area of the cylinder is. Okay, which is just basically a circle with some height on it. Okay. Now, if we were going to look at something slightly more complicated, we would look at figure 2 here. Okay, and what figure 2 is doing is saying, instead of taking a horizontal line segment and rotating it about the x-axis, now we're going to take a line segment that has some slope. In this case, I'm using one with a positive slope, and we're going to rotate this about the x-axis. Okay. Again, the principle is the same. We want to take that particular that function, rotate it around the x-axis to form a surface of some shape. And of course, you see that this shape kind of looks like a lampshade. Okay. Now, the formal name for that mathematically is a circular frustum. Okay. And so if you never heard of that word before, that's fine. And I'll go ahead and write it for you here. Just frustum. Okay. And that's let me try to do that again. That's a R-U-M that I was trying to write there. So a circular frustum, that's the proper name for it. So the idea here is that although this looks like a lampshade that we're kind of cutting and rolling out, which will look like this if we do it, it turns out that it still will end up looking like a rectangle. But the thing is that this y value here, or what is going to be considered our radius for this frustum, is going to be the average of this smaller radius and larger radius. Okay, Now, we can get into a whole lot of detail on why that is. But simply put, if I was to take this top curve here, which is 2 pi y1, which is basically this small circle here cut and rolled out, and take this curve here, which is 2 pi y2, which of course is the circumference of this larger circle on the end of the circular frustum. We cut and roll that out. If we rolled it out, it would look something like this. And I'm going to change colors here so that you can kind of see what I'm saying. So if we took out this first one here, if we rolled it out, it would be something with a length like that. If we took this one and rolled it and straightened it out, it would look something like this. Now, this length L here and this length L here is going to be the same, but notice that we can adjust this top length and this bottom length to the point to where there is another length L that we can attach here and we can attach here, so that this basically looks like a trapezoid. Now, if we're looking at this as a trapezoid, then one of the things that we know is that the area of a trapezoid is essentially 1/2 the height of the trapezoid times the sum of its bases. So, and normally we'll write it like this. Well, we'll say there is a smaller base plus a bigger base, okay? And so here, this would be the height, this would be your smaller base, this would be your bigger base. Now, if we took this trapezoid and we laid it on its side, it would look something like this. And notice that the bigger base now looks like our y2. The smaller base looks like our y1. And of course, the height of it is now the width of it. Okay. So my point here is that this circular frustum, if we were to roll it out and rearrange it, is basically going to look like this trapezoid here. And if we replace the little b and big B with y1 plus y2, then that is essentially what this y star ends up being. Okay, it's just the average of y1, which is the smaller radius here, y2 divided by 2. And of course, the divided by 2 part would come from the 1/2 from the area of the trapezoid. Okay. So the main thing that I want to get across here in both of these examples is that in either case, in order to figure out what the length, well, not what the length is, but what the surface area of the shape that it makes with the function that we use to rotate about the x-axis, it both came down to a matter of just using what the circumference of a circle is. Okay. And so here, if we look at the surface area just essentially was what is the distance around the circle, which we know is circumference, times the height, or in this case, the length of PQ. And so here, whether it was like this, or we had it using the circular frustum, once we worked everything out, in both instances, this just looked like a rectangle, where this part here and this part here is basically the circumference of the circle. And of course, this part here is going to be the height of the cylinder. Here, this is the height of the frustum. Okay. So now we've seen these two simple examples, but what do we do when something doesn't look this easy as far as the function being like a straight line? What if we had something that kind of looked curvy like this, and we wanted to take that and rotate it about the x-axis and form a shape? What would that look like, and how would we go about actually coming up with a formula to be able to find the surface area of the shape that's made by a function that looks like that? That's what we're going to talk about next. So if we consider this solid of revolution for a function f of x, and this function is starting here at x equals a, and it's stopping here at x equals b. And just to make sure that you can see the actual function I'm considering, I'm going to go ahead and put all of that dotted lines in red. Okay. All right. So we're taking this function that I've dotted in red here, and we essentially are going to rotate it about the x-axis. And when we do that, you see that we have the shape that we make, and it basically looks like the outer surface of some kind of some container, okay, like a vase or something. Okay. Now we want to know, well, how do we find out what the surface area of this particular shape is going to be? Well, it turns out we can use similar thinking to what we did in figures 1 and 2 earlier, but we're going to have to bring in some of the thinking that we also did when we talked about the concept of arc length. And so for those of you that are kind of watching these videos that I'm doing in order, you know that we normally talk about arc length before we talk about surface area. And so some of the thinking that went along with that, and using the mean value theorem and such, the same kind of thinking goes into trying to form the formula that we'll need to know for this particular situation. So the idea is this. So instead of trying to look at the entire function here as a whole and rotate it, what we're going to do is look at a small piece. Okay, so we're going to look at this small piece here, and we're going to call that piece a band. And so the idea is that we want to pick a band that is small enough to where this this curve right here that you see from P to Q, the idea is that if I pick a band that's small enough, even though this is curved, it's actually going to look like a straight line because it's so small. Okay. And so what we want to do is theoretically figure out, well, what would that actually look like if I picked a band that was so small that I could characterize it as a straight line, figure out a formula for being able to find the surface area of that small band, and then just say, hey, I have an infinite amount of these small bands from x equals a to x equals b, and just add it up. And so in general, that's essentially the thinking that goes behind coming up with this surface area formula here. Okay, so I'm going to go through a little bit of the theory, not much, so that you can get a general idea of what's going on. And then after that, we'll introduce the formula and then do some examples. All right, so again, the idea here is that we want to take this small portion here and zoom in on that and examine that situation. Okay, if we zoomed in on this situation here, what it would look like is what you see here in figure 4. Okay, and just for clarity here, this got kind of cut off, but this should say y of k minus 1. So we'll refer to that a little bit later. So here in figure 4, if we zoom in on this small band around the surface of the solid of revolution from figure 3, it shows here that this segment PQ here has a length that's going to be approximately equal to L. And think of L as if we were trying to use some really small straight edge to lay on figure 3 here. So let's say we had a ruler and it was really small, and we were trying to lay it on the profile of this particular function here to say, all right, well, how many miniature ruler lengths did I have to count to get from A to B? And of course, if I add all those up, then that would let me know how long that particular, that would let me know how long this is. But if I'm just looking at this area from P to Q, this length from P to Q, then I would take that as, hey, that's one miniature ruler length, and I'm going to figure out, well, what is the surface area that's associated with that particular small ruler length area, rotating that about the x-axis. So that's what you see here in figure 4, me sort of setting up what I would need to do to do that. Now, notice that length L, along with the change in y values and the change in x values, form a right triangle. And if it forms a right triangle, then we know that the relationship in between three sides of a right triangle is such that, of course, we know that a squared plus b squared equals c squared. Okay. Again, that's better known as Pythagoras theorem, but Pythagoras didn't make it up, so I won't be calling it that. So here, if we keep going, if we look at figure 5, what figure 5 does is it actually looks at this and says that, hey, guess what? Since this small curve here from P to Q is part of my function, f of x, and that piece on that interval from x of k minus 1 to x of k is smooth and continuous, what that also means is that it is differentiable. Okay, so now I'm bringing in the calculus 1 or the cal A to this. And one of the important theorems that we learned in that course is the mean value theorem. Okay, and that theorem states that if I have a function that is smooth and continuous in some closed interval, and it is differentiable for every value strictly in between these n values here, then there exists at least one real number strictly in between this x value, x of k minus 1 and x of k, such that if I identify it, the slope of the tangent line of the point on that function at c sub k is going to be the same as the slope of the secant line going through points P and Q. Okay, so the reason why that's important is because if we look at our right triangle here, I'm going to change colors here so that I could draw it in a different color. So let's go with, I'll go with green here. So we look at this right triangle that I'm drawing here. You'll note that one side is delta y sub k, another side is delta x sub k, and that's just the change in x values, change in y values, and then of course you have L. Now, if we were going to express L, we would want to try to express L in terms of just x values. And so we are using this mean value theorem to help us to be able to do that. Okay. Now, the mean value theorem basically guarantees that this equation could happen for this function that's from point P to point Q, because the function is continuous and differentiable. Okay, and it's smooth as well. So here I know that the derivative, or let's say the slope of the tangent line at x equals c sub k is going to be the same as the slope of the secant line. Okay, and so in using this will help us to be able to sort of rewrite our formula that we're going to have for the surface area of this small band in terms of just the function f of x and delta x of k. Okay, so let's go ahead and move on now and sort of build this formula. All right, so notice that if the function that we're dealing with is going to be non-negative, which basically means that we know that that function lies either on or above the x-axis for all the x values that we're considering here, and it's differentiable, which means it's going to be smooth and continuous, then we can assume that this length L that we're using as our miniature ruler to measure out pieces of f of x, so we can use that to approximate the length of the curve of this particular curved segment. Okay, so if you remember back up here in figure 5, essentially what I'm saying is this. Let me erase this part here. So essentially what I'm saying is that this curve that we have here from from point P to point Q, if we pick this curve to where it's so small that even if we zoom down, this small curve looks like this straight line here, okay? So what we're going to do is assume that this curve PQ is so small that it still kind of looks like a straight line, okay? So if we do that, then of course we have this situation again that we had back in figure 2, okay? And of course, this forms a right triangle. We know this side is the change in y values. We know this side is the change in x values. And we know that, of course, that length there is going to, theoretically, we can get the curve segment PQ to be small enough. It's going to be the same as a straight line L here, okay? So in that, if you remember, the formula that we have for the surface area of a small band is going to be this pi times the sum of y1, y2 plus L. And if you forgot that, I'll go back to the circular frustum that we talked about to show you that. Okay, so here is the formula that I was talking about. And remember how, and I'm going to go back some more to the circular frustum. So remember how this circular frustum here, we took it, we broke it out, said it pretty much looks like a trapezoid, and in doing that, we know that this trapezoid here, if we wanted to simplify it even more, we could call the little base plus the big base divided by 2. We can just rename that y star. And of course, by having that, we know that this circular frustum here will pretty much look like a rectangle, okay? If we simplify some things, and that's basically what this particular shape here is representing. So my point is that if we have 2 pi, and then we substitute what y star is, which is going to be the y1 plus y2 divided by 2, and then we have L there, then we see that these 2's reduce to 1, and we have pi times y1 plus y2 times L, okay? So that's where we got that from. So now that we know where we got that from, here we know that our y sub k could also be looked at as f of x sub k, because y sub k is going to be the corresponding y value for the x sub k value. And the y sub k minus 1 could be looked at as f of x sub k minus 1. And here we can replace y1 and y2 if we want to look at it this way. If we let let's say k equal 2, then this would be y2 and this would be y1. Of course, if k is equal to 2. So if we look at it that way, then of course this is the same as your y2, this is the same as your y1. So we're replacing y1 and y2 with just f of x sub k minus 1 and f of x sub k. So now that we have that established, we also know that L is just going to be the hypotenuse of this right triangle here, okay? Which is essentially just the change in x sub k squared plus the change in y sub k squared, take the square root of that, okay? And that is what you see right here. So this is just our representation for L. And again, I kind of write all the stuff down here. So now that we have all that in place, now what we can do is say, all right, well, I got a formula for the kth surface area band for this function going from x equals a to x equals b. Now all I need to do is to take this band and add k of these bands together, okay? But in reality, what I really want is to have those bands PQ to be so small that I can actually fit an infinite amount of them. Okay, so we're going to say, you know, as n, or maybe, yeah, so as n goes to infinity. And so we're assuming that the value, or the letter k that we're talking about, is a specific value of n. Okay. All right, so at this point, we need to kind of regroup and think about, all right, well, where are we trying to go to wrap this up? Okay. Right now, we're trying to get a formula for the surface area of this small band. And notice that here we have a function. We have our function f of x. We have our function f of x here. And we also have things in terms of x of k and y sub k. Now, since this is in terms of x sub k of something and x sub k here, and this has x sub k in it, we would desire to have this delta y sub k being expressed in terms of x sub k if we can. Okay, and if you noticed, the mean value theorem, which guarantees that this is true for that kth interval that we were talking about, if our function is smooth and continuous in that closed interval from x of k minus 1 to x of k, and differentiable for values strictly in between x of k minus 1 and x of k. So we could rearrange this particular equation here to rewrite delta y sub k in terms of the derivative of our original function f of x at this value c sub k and delta x sub k. And so if we look here, that's essentially what we're doing. And so when I go and take delta y sub k, plug it in, I get this. And then from there, it's just a bunch of algebra trying to get to what this final formula is going to be. And so you can see the algebra that's being done there. Eventually, we get to here. And we see that since L is going to be all of this, then I just rewrite it. So all of this is just this part right here. And then, of course, remember this was my y1, that was my y2, and of course I had the pi out here. And so this would be the formula that I would use for that very small kth interval to figure out what the surface area of that band is. Okay. Now, the idea is that I want an infinite amount of these depending upon what k interval I'm on. Okay. And I want to take an infinite amount of those and just add them together. Okay. So if I do that, then of course, now I'm looking at something that looks like a Raman sum. So I want the values of, I want all these k intervals from the first one down to the nth one. Okay. And so I know that if I can get n of those, however many of those little small miniature rulers that I want to use to be able to measure the actual length of the small portion, the curved portion PQ, that is what n would represent. Okay. And so, of course, ideally, what I would want is for n to go to infinity, because I would want that small curve segment PQ to theoretically be as small as possible. And to do that, I would have to, make the number of those rulers that I use be an infinite amount. Now, if that happens, then notice that this value x sub k and x sub k minus 1 will continue to squeeze towards each other. And of course, it'll be more like this. X sub k minus 1 is here and x sub k is here. This will keep getting bigger. This will keep getting smaller, so that they eventually converge upon some value in the middle here. And that value in the middle that we're going to assume that it's going to be is this c sub k that we talked about earlier. Okay. So that is the basic idea. Now, of course, we want the behavior as n of these little small rulers are acting on this formula for the surface area of the band. And you can see by using definitions of what a definite integral is and how we change the Riemann sum into an infinite summation here, or an integral. We see that we end up writing this formula this way. Okay. Now, I note here that in reality, my x of k minus 1, and the value that's supposed to be in it, c sub k, are not actually equal to one another. But remember, the idea is that as n approaches infinity, theoretically, these three numbers are all going to converge upon each other, so that when n, and I know this is kind of a sort of an incorrect statement, but I'm going to make it here just to make my point. If n could actually equal infinity, then that means that x sub k would be the same as x sub k minus 1, which would be the same as c sub k. Okay? Or I probably want to write it this way, kind of make it look like the order that it's supposed to be in. The x sub k minus 1 would be equal to c sub k, which is x sub k. So, because again, this number here would try to get bigger, this number would try to get smaller, and of course these two would converge upon this one. So that's the basic idea. And so because of that, even though this is technically not true, from a theoretical standpoint, that's what we are approaching. So here we make the assumption is that if n could go to infinity for real, then this would be our formula for the surface area of the whole entire shape that we are trying to form from x equals a to x equals b. So because of that, we see that our formula here, we conclude that our formula is just going to be surface area of the whole shape, and that's why I have whole there. And I have the x in the subscript there because we're rotating our function f of x about the x-axis. And so this would end up being our formula here, just 2 pi times that function, square root of 1 plus the derivative of the function squared, all that multiplied by dx. And of course, definite integral from a to b. And if we think of f of x as being a y value, then we could think about it as 2 pi y square root of 1 plus dy over dx squared. Now, if we were rotating about the y-axis, then it's the same principle, but we just need to change the variables here. So our independent variable will now be y instead of x. And of course, really doesn't make a difference here, but I've named the limits of integration different just to notate that, hey, we would have these points AC and another point BD, and when we rotate about the x-axis, we pay attention to A and B. When we rotate about the y-axis, we pay attention to C and D. All right, so this is basically it. So we've taken a while to actually show you how we actually come up with that formula, but now that we know what that formula is and how we come up with it, we're now going to use it in some examples.